Okay, so let's get started. We're going to be taking a look at doing an overview of our model fuel equation mode and tuning strategy within the Link G5 and G4X programming. Now, the model mode is primarily what I stick to for calibrating and tuning with the Link. There are two primary fuel equation modes that we can actually work with: traditional and model. We're going to have a separate training module, actually a couple training modules on working in traditional mode coming up here. This is going to be dedicated for this tutorial and a few other tutorials to the model mode, setup, strategy, just making sure we understand all the little details with the model mode. Now, there are advantages to both. The traditional simplifies tuning and calibrating. The model allows us to have a lot greater accounting for variables within our fueling calculation. So we can account for changes in our fuel, so the fuel density. We can account for the fuel temperature. We can count for any kind of elevation changes. So there's a lot of advantages to tuning in the model mode compared to the traditional. So let's jump in here and take a look at what we have going on within our model mode in our airflow air mass strategy. So what we have here, we can take a look under fuel equation mode. I have it turned on right now to model from traditional. So when you usually open up your file, most of the base files will be set to traditional. Link does this because it's an easy way to calibrate and tune within the system. Now, easy is sometimes good, but oftentimes taking the easy way out, you're not going to be able to account for all the variables, and you'll find you won't be as consistent in your fueling, and you can't kind of take into all of the variables into your fueling calculations. So you can't bring in fuel pressure, for example, in the traditional mode. You can't bring in directly calculate air density in your traditional mode. You can go a roundabout way to account for that. So Link likes to keep things simple. So you'll open up a file, you'll probably find it set in traditional. Let's go change this to model here. And we do this, we find there's a lot more parameters to go in and deal with. So we have engine capacity we have to enter in here, fuel density temp coefficient. We have fuel charge cooling coefficient. So all of these variables are accounted for on top of a couple additional things in order to calculate a proper amount of injector pulse width that we want to send to the injector to spray the fuel into the engine. That's at the end of the day here, when we're looking at the traditional or the model, we're telling the injector to open up a certain amount to spray a certain amount of fuel. It's just how we go about getting to the same end result is completely different between these two different fuel equation modes. So the model accounts for a lot more variables, definitely a lot more complex, and it gives you a more consistent, repeatable calibrating method compared to the traditional, in my opinion. So let's break this down a little bit further so we understand what's going on here. So kind of more of a big picture right now, and then we're going to get into a couple specific things. So what we have coming onto the screen here is an equation that's going to be fuel mass is equal to air mass divided by target air fuel. This is the underlining fuel and airflow model equation in the model strategy. Now, fuel mass, air mass, these are probably terms you haven't heard of before. Let's break this down a little bit further so we can understand this conceptually, what mass actually represents. So mass is going to be the volume times the density. The best way that I like to describe this is going to be if you have a cup and we know the volume of the cup, and we fill it up with water. We know the density of water. We know the volume of the cup. Therefore, we would know what the mass of the cup would be. Now, dump out the water, fill the same cup up, so the volume hasn't changed, fill the same cup up with gold. Density of gold is a lot greater than the density of water, and therefore the mass is going to substantially increase. If we pick up the cup full of water, we pick up the cup full of gold, they're going to be completely different masses, and we can feel that physically as we actually pick it up. Now, carrying that concept forward, let's take a look at our air mass. So when we're talking about air mass, it's going to be accounting for the volume of air entering our engine and the density of the air entering our engine. Now, volume is easy to conceptualize. So we know if the throttle opens, we're going to have a certain amount of airflow coming into the engine. The density is something that is a little bit more difficult to picture because we physically can't see air density changing, but it does change with temperature and elevation. So when we're working in the Link, we can account for the density of the air. And this is important because if we're talking about really hot air or at really high elevations, so we're not at sea level, let's say we're at 5,000, 8,000 feet of elevation, there's going to be less density to the air and therefore less oxygen molecules packing the same volume of air entering our engine. What this is going to do is require less fuel. So less dense air needs less fuel. more dense air needs more fuel. And working in the model mode allows us to actually characterize air mass changing. Now, how do we actually do this? How is air mass calculated? Well, we can think of the model mode as a simulated way to be able to have the same kind of measurement that we would have with a mass airflow sensor. So mass airflow sensors are used by most OEM manufacturers. You typically fit it to the intake that's going to where the air is going to be drawn into the engine. The mass airflow sensor can directly measure the amount of air mass coming into the engine in steady state conditions. It's very, very accurate. When we're talking about the model mode, we're estimating the air mass. So theoretically, if we had a mass airflow sensor fitted to our engine, and we also were working in this air mass strategy, we would find the measured air mass from the mass airflow would match the estimated air mass, if everything was accounted for correctly, coming from the calculation within the air mass strategy in the model mode. Now, how do we actually come up with that estimated air mass?
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.